You've been exposed to radioactivity. How can you tell how much? How can you tell how much radioactivity have I been exposed to? Well, most of the time, we don't care. If you're an average person living your average life in your average home with your average medical concerns, you don't need to worry about radioactivity at all. If, on the other hand, you work in a situation where you are around highly radioactive materials, or you are perhaps have some kind of medical condition where you have to have quite a few X-rays or PET scans or something like that, then we want to measure how much radioactivity you've been exposed to. And so there's two ways we can do that. There's a passive way and there's an active way. The passive way is really, it's something that you wear on your person that detects how much radiation you've been exposed to by detecting how much radiation the badge has been exposed to. These are film badge dosimeters. The way this works is you have this badge, and you wear this thing all the time when you're at work, anyway, if you work around radioactive materials. And the badge is not really detecting how much radiation you've been exposed to. It is detecting how much radiation it has been exposed to. The idea being that if you are a good employee and you wear it all the time, then whatever it gets exposed to, you are also exposed to. And so the way these things work is actually pretty simple. They have some fancy photographic film inside of this plastic container, and it cannot get exposed to light because it is completely enclosed inside the plastic container. But, as we talked about earlier, high energy radiation can pass through materials. And so even though it cannot get exposed to visible light, it can get exposed to radioactive, the particles coming off of radioactive decay. So things like beta particles and alpha particles can actually penetrate that plastic, although alpha particles not quite so much. It's mostly gamma rays and beta particles that we're detecting here. And so it is actually, the photographic film is, what's the word? It is developed as it gets impacted by that highly energetic radiation. And so the badge is actually just kind of monitoring how developed that photographic film is. And so it can gauge how much radioactivity you've been exposed to by how developed the film becomes. And so usually how those things work is you have a certain amount of radiation that you're allowed to be exposed to over a certain period of time. So if you work at a nuclear power plant, for example, you might have, I forget what the actual number is. There is an actual value, a number of millirems that you're allowed to be exposed to over a 6-month period, I believe. Or maybe it's a year-long period. Regardless, there's a certain time period, and if you get exposed to that amount of radiation, then you're done for the rest of that time period. So if something really needs to be worked on in an area of the plant that isn't quite as well shielded as some other area, and you're in there for longer than you really should, and this really would never happen. There's too many safety regulations in place. They'd have not just one person working the whole time. They would swap people out so that they wouldn't get exposed to quite as much. But if, just for example, someone had to, for some reason, work in an area where there was not as much shielding as in other areas, and they reached their allotted amount of radiation exposure, then they would essentially get paid leave for the rest of the 6 months because they would not be allowed to work. Or at the very least, they wouldn't be allowed to work in the plant. Like, they might still have to work, from home, as everyone is doing right now, but they would not be able to do what they were before, where they were exposed to radioactivity, because they had reached their allotted amount for that time period. And once the time period is passed, they can go back and do what they were doing before. A more active way of measuring radioactivity is using a Geiger counter, or more accurately, a Geiger-Müller counter. Poor Muller did not get his or her, actually, I'm not sure if it's a man or woman, name mentioned very often, but it is technically a Geiger-Müller counter. The way this thing works is you have an inert gas inside of the container here. And there's a very thin window here that allows particles to pass through it if they're highly energized, like radioactive particles. So just regular old gas can't really get through there. But it's thin enough that alpha particles can get in, beta particles and gamma rays definitely can get in there. And that high energy radiation, when it penetrates the thin window, it's probably going to bump into one of these inert gas molecules that are inside of there, which is usually argon, and it's going to ionize that gas. And when it becomes ionized, the ionized particles are attracted, the positive ones to the edge of the Geiger counter, and the negative particles, which would be electrons, are attracted to the cathode there in the post in the middle of the Geiger counter. And so if you've ever seen in the movies where they have the Geiger counters and it starts to make that ticking sound, those ticks are actual detections of radioactivity. That tick is the sound of an electron impacting the cathode. And so that means that something was high enough energy to get through that piece of plastic there, or glass, or whatever it is, and ionize the gas inside. So this is a much more active way of measuring radioactivity. It has to be turned on, and it's measuring the radioactivity right at that moment, whereas the dosimeters are measuring, how much did you get exposed to over this entire period. Let's talk about the bomb here for a minute. So the bomb was actually first discovered, it was kind of a group of scientists that all came to the realization that radioactivity and this effect of an unstable isotope decaying and giving off a lot of energy could be made into a bomb. The way that it was realized that it could be made into a bomb was through what's called a nuclear chain reaction. So this is when you have an isotope like uranium-235, and if you cause it to decay essentially unnaturally. Now, it would eventually naturally decay, but if you want it to decay faster, what you can do is you can smack it. So if you shoot a neutron at it, and that neutron gives it a good smack, that force of that impact will cause the nucleus, which was unstable in the first place, to go ahead and split. It will break apart. And when it does that, it makes two new nuclei that are at the very least more stable than the original one. And notice here that the nuclei that it breaks into are very different. This is a very different nuclear process than the alpha particle, or alpha decay, beta decay, gamma decay that we saw before. This is not alpha decay. This is literally splitting the atom. It's breaking it into pieces. It's not just the nucleus spitting something out. So it is a whole different beast. It's similar in that it's a nuclear process, but it is a whole different beast in that the process is very, very different. So we shoot the neutron at this uranium-235. It breaks the nucleus apart. When it does that, it's going to make more neutrons. So not only does it make these two isotopes here, which may or may not be stable, it's going to make more high-energy neutrons. Because if you remember the uranium-235, it had a lot of neutrons. It needed a lot of neutrons to hold it together. These don't need as many neutrons to hold together, and so those extra neutrons essentially get spat out as more high-energy neutrons that are then available to go smack into more uranium-235. By the way, this is showing it as each time is producing 3. It doesn't always produce 3. Sometimes it's 2. It's not a truly random process, but it's not the exact same every single time. But it is most of the time 3 for uranium-235. So those 3 neutrons bust up 3 more uranium-235s, which then produce for each of those 3 more. And so you get this giant cascading effect of uraniums breaking apart The key thing for realizing that this could be weaponized was when it was realized not only could you have this chain reaction, but every single time these things break apart, you get this. That is supposed to represent energy. It's giving off an enormous amount of energy. Now, for each individual atom, it's not all that much energy. But when you have a giant cascade of them, where you have literally trillions upon trillions upon trillions, upon quadrillions of atoms doing this in a split second, you take a relatively small amount of energy given off by one atom, multiply that by a few trillion quadrillions, and you get this. Oppenheimer, who was the designer for the first atom bomb, when he tested the first bomb, which most people don't realize actually, the first nuclear explosion actually happened in the US. We actually did one test of the bomb before we dropped the 2 bombs on Japan. So there was actually a nuclear explosion, I believe in Nevada. It might have been New Mexico, but I think it was Nevada, where they tested a bomb, and he quoted this Hindu scripture, "Now I am become death, the destroyer of worlds," because he realized this was really something extraordinary, and by what I mean by that is extraordinarily dangerous. Extraordinary as in world-changing, not necessarily in a good way. And believe it or not, the bomb that they tested that caused him to say this, it's like 1,000th the power of bombs that we have today. It was actually relatively small compared to what we have available anyway today. So much more peaceful, much better use of this enormous amount of energy that is released when an atom splits is nuclear power. And I am a huge proponent of nuclear power. I love nuclear power. I gave a whole hour-long talk about how nuclear power is the best option the world has for clean, cheap energy at this point. So I'm going to try to keep this to a minimum here, because I could, like I said, I could go on for at least an hour talking about nuclear power. But most people kind of have a misunderstanding of what a nuclear power plant is. Most people, at least I, before I actually started doing research on this, I kind of thought that, they must have like a little mini nuclear bomb, like it's like the movies, like there's some glowing thing and they're just kind of siphoning the energy off of the glowy nuclear thing. And really it's just a glorified teapot is all it is. So if you remember, nuclear materials are naturally hot. So if you take uranium and you enrich it to a certain point where there's a higher percentage of uranium-235 than in just normal uranium, because the uranium-235 is unstable, more so than the 238, it is just hot. It's naturally hot because it is decaying slowly with time, and that decay gives off heat. And so those materials are hot without us having to do anything to them. We don't have to put energy into it. We don't have to, to give it gas to go or anything. It is just naturally hot. It is hot all on its own. And so what we can do is we can take that naturally hot stuff, run some water over it, and boil the water. And in that boiling water, that steam from the heat from that naturally radioactive material will then turn a turbine that produces electricity. This is actually the exact same overall process that we use for coal plants and natural gas plants. The only difference is the source of the heat. So in a natural gas plant, which is what we're more and more going to, which is not ideal but is certainly much better than coal, natural gas plants, The only difference is instead of having nuclear material just sitting there that's naturally hot, heating up the water, they pump in methane and burn the methane to get the heat. But everything else is the same, like the taking the heat, boiling water, turning it to steam, causing the steam to flow through a turbine, which then turns the turbine to produce electricity. All that's the same. The only difference is the source of the heat. There are a lot of different designs for nuclear reactors nowadays. Not a whole lot of them have been built just because people are kind of terrified of nuclear power, which is a shame. But one of the older models uses these fuel rods and control rods, and it is an older model, but it is by far the most common just because most of the reactors that have been built were built 40 plus years ago. Well, maybe not quite that long, 30 or so years ago. 30 plus. You have the fuel rods here that are, again, naturally hot. They're very hot on their own. And to keep them from melting down, number one, you can just run water over them. So again, you run the water, which acts as a moderator as well as a coolant. The moderator meaning that it not only does it, in terms of temperature, cool the rods down, but it also keeps the neutrons from going a little bit too crazy. So it keeps them from getting hot, both in terms of the water being cooler and in terms of limiting the breakdown of the uranium. But in addition to that, you can also have these control rods that you can drop in there between the fuel rods that are essentially neutron sponges. And so if you do that properly, and if you have it built correctly, if something goes wrong, those control rods drop in there and they soak up all the neutrons that are causing the material to be decaying at a higher than normal rate. And the fuel essentially doesn't completely shut down because you do still have the natural decaying occurring, but any decays that are caused from, this one uranium decays and it gives off a neutron, which then comes over here, it essentially gets blocked from getting to another uranium because there's that control rod in the way absorbing the neutrons. And so it slows the reaction way, way down. By the way, the reason that Chernobyl was such a disaster, like there was lots of reasons, but the main reason that it exploded anyway, instead of just melting, the main reason it exploded is because they had their control rods designed improperly. They had carbon at the tip of the control rod, and as soon as they started to drop the control rods in, they realized something was wrong, and they were like, okay, drop the control rods in, we need to slow this down. Because they had carbon at the tips of the control rods, what they didn't realize was that carbon, they had used it for some other secondary reason. They didn't realize that the carbon would actually speed up the process. So once the rest of the control rod would get in there, it would have slowed it down, but because the carbon was at the tip of the control rod, as soon as the control rods entered the material, it didn't slow it down, it sped it up. So it was already running away. They dropped the control rods in, the carbon at the tip speeds up the process, and it just explodes. So we do not have carbon-tipped control rods anymore. It was just a very bad design flaw. Soviets were known for a lot of things, being amazing and engineers, and especially amazing in terms of safety in their engineering. It's not something they were known for. So around the world, France has a lot of nuclear power, which is the main reason why their power is so cheap. They have very cheap. France is actually almost. It's about 90, I guess about 90% green in terms of its energy production. The vast majority of that is nuclear. The United States has a good bit of nuclear, but it's actually decreasing, which is very unfortunate. The amount of nuclear is decreasing. In China, it's actually the opposite. China has a whole lot of coal. I don't know if those percentages are accurate now. This is kind of an older graphic, but it still does have the vast majority coal, but it is trying to ramp up its nuclear. One of the things that a a government like China has, since they don't have to really care what their people think when they make decisions, is they can just decide we want to do nuclear, and even if the people are scared of it, they can just do it, which is not necessarily a good thing. But worldwide, about 15% is 15% of the electricity produced worldwide is nuclear. And I hope that someday it will be a lot more than that, because it is a very, very safe technology, especially compared to other things. Believe it or not, in terms of gigawatts of power or terawatts of power produced, nuclear is actually safer than even solar. And if you're thinking, what the heck, how is solar killing people? In terms of lives lost, nuclear, even with like Chernobyl taken into account, nuclear is safer in terms of lives lost than solar, because believe it or not, installing solar panels is not a really safe thing to do. People fall off of roofs and things like that when they're doing that, and that's not even taking into account the environmental effects. Because there's a lot of really nasty chemicals in solar panels that just go into the waste stream once they are used up. Anyway, like I said, I could talk for an hour or more about that. Let's move on to the last little thing here, and this is how radioactivity is used in medical settings, as well as some chemistry settings. So radioisotopes can be very useful in certain kinds of chemistry. So if, for example, you want to track what happens to a specific atom in a specific molecule during a reaction, what you can do is, so for example, if you wanted to track a carbon in an organic chemistry reaction, and you wanted to know this carbon right here, I think that carbon, so this is kind of a silly, simple example, but so we had some ethanol, and if for some reason you wanted to know, is it this carbon or this carbon that reacts in this reaction that I'm interested in, and I want to know which one. I don't know, again, this is kind of a silly example, but if we wanted to know which one was which, we could put one of these to be just regular old carbon-12 and the other one be carbon-14. And so then we could, and there's ways you can do that. There's ways that you can make sure that one of them is carbon-14 and the other one is carbon-12. And so you could then have this molecule, which with two different isotopes, run through a process, and then you could check your product at the end. Sorry about that, had to cough. You can check your product at the end of the process, and you can see, does my product have carbon-14 in it, or does it have carbon-12 in it? And so you can actually figure out which carbon in a molecule is the one that's actually reacting. It might tell you that it's one versus the other, or it could tell you that actually it's just completely random. Sometimes it's one, sometimes it's the other. Still good information. Radioactivity is also very useful for medical procedures. So for PET scans, for example, the way that a PET scan works is you put in a radioactive isotope into the body. In this case, it's going to the brain. And when that radioactive isotope decays, it will emit a positron. So PET scans are positron emitting, what's the T? Transmography or something like that. I forget exactly what the T is, but the T is essentially describing the process. So it's positron emitting trans something, I think. Anyway, so you have that positron emitter that's somewhere in your body that's attached itself to maybe cancer cells or something like that. It's been attached to something that will preferentially go to one place or another, and you want to track where those things are going, and so you can use the PET scan to do that, because when the positron is emitted, it's going to very, very quickly find an electron, because there's electrons everywhere. There's very few positrons anywhere. The positrons only exist for a fraction of a second, because as soon as they collide with an electron, they annihilate each other. And when they annihilate each other, you get a pair of gamma rays that go off in opposite directions. And so you have these gamma ray detectors set up all around your body like this. And they can actually detect based on how quickly one gamma ray reaches one side versus the other, up and down, and then as well as left and right, just depending on which detector detected it. And so you can get actually a really good scan of a person's body that way, and where those particular isotopes have gone in the body using a PET scan. But PET scans are kind of a, if there's no better option, that's what you go to is a PET scan. You're going to utilize every other option before you go to a PET scan. Because as you can imagine, it's not necessarily the best thing for your health to have gamma rays shooting out of your brain. It's better than dying, but so depending on what your prognosis is, the doctors might be like, actually, a PET scan is not really worth. You're not going to get a PET scan to help you figure out if you what kind of allergies you have. Not that that's possible to do with a PET scan, but like it's not necessarily something that would be a reasonable trade-off, the risk of a PET scan versus something that's just kind of an annoyance. But if you have something that's causing you a lot of pain, or something that could kill you, and the only way to get a good idea of what's going on is to use a PET scan, well then you probably would go ahead and say, well, it's not the best thing to have gamma rays shooting out of your brain or out of your stomach or wherever you're doing the PET scan. But it's better than the alternative, and so we'll do it. So that is it for this chapter. Sorry this video went a little bit long. Be sure to write down any questions you have, and we will talk about it next time we meet.